Hi, I'm Tzvi and I lead the Israeli research labs of the NEC Corporation. I gave a talk about this subject at ODSC Europe 2019 to a live audience, and I do hope we can all meet again in person next year. Now, when I give this talk in front of a live audience, I usually ask how many of you are involved in developing or deploying a machine learning or deep learning model that is being used by an actual customer versus being published academically. The emphasis is not on the commercial viability or importance, but on whether there is someone who must rely on the model results and performance to achieve some actual actionable goal. I will make the point that explainability is much more important, indeed critical, when you do have such an end customer. Before I start, I will make two promises. First, I will show how, in certain cases, you can use explainability to actually improve future model performance, or at least put bounds on your model performance. Two, since this is pre-recorded, I measured my time and I will finish ahead of time. Okay, so first, a few mandatory words about NEC. Like so many tech companies, NEC originated as a startup by a founder who left another startup. In the photo, you can see the guy on the left. He worked in the startup of Thomas Alva Edison and then left to start his own startup in Japan. 121 years later, I believe we can say both startups have done rather well for themselves and for their founders. Since its founding, NEC has always invested in core research. As this is ODSC, I will not bother you with the discovery of carbon nanotubes or the building of the first spacecraft to orbit an asteroid and the first one to actually take samples from one and return them to Earth. I will point out to the video in the middle upper row, made by a young researcher in our Princeton labs in 2003, about 10 years before the famous ImageNet paper was published. This researcher had the idea to apply convolutional neural networks to detect people in a video. Very new idea at the time. You can still find this clip on YouTube. That researcher was Yann LeCun, a name you may have heard once or twice. And he recently got the Turing Award for his work on AI. The point I'm trying to make is that AI was around and was being used, including convolutional networks and what you may call deep networks, well before all the hype started. And thus, NEC got to use AI to serve customers and learn the realities of this field. Now, customers, unlike academic reviewers or referees, do not care so much about state-of-the-art or about area under the curve. They do, of course, but they care much more about practical explainability. That means they do not care that some dataset is the one everyone uses. They have their own dataset, which is always noisier, smaller, and not as all-encompassing as we would like. They also do not care about numbers. They want the AI to be preferably better than people, but also like people. And that is the key source of the need for explainability. Now, this is the main message of the talk, so I will repeat it a few times throughout the talk. Useful explainability gives you two things. One, a sense of in which situations your model does better or may fail. Two, an indication of what you can actually do to improve your model in the future. This is important, so I will phrase it again in a different manner. Useful explainability is not like philosophy. It is more like debugging. It may not give you the good feeling you understand your model, but it will give you tips on how to improve it and when you can expect it to fail or succeed. So now to a quick recap of why we have all this deep learning and AI hype. The two main precursors that started the wave were financial success in the online advertising and recommendation engine markets and the scientific success of ImageNet in image recognition tasks. On that, I will have to make a note. In the last few years, there are claims that the latest deep learning models have exceeded human performance on the image recognition database. I do not think that is true in any real-world sense. Those networks may outperform an average human statistically on distinguishing some dog types or flowers, but they will still make mistakes that even a 4-year-old will not make on much simpler examples. They may be statistically better than us on some carefully crafted categories, but they are far worse than us on plenty of simple real-life images. And I referring that to my note about customers or end users. They don't like it when your system mistakes a duck for a battle cruiser. They don't understand why it did that. On the other hand, recommendation engines and online targeted ads are a perfect application for models which you may not understand, yet can demonstrably reach a higher success rate and, even more importantly, continuously adapt to a complex and rapidly changing landscape. As long as the yield, clicks that monetize or content consumed, is higher than that of the alternatives, we are willing to use the most complex and black box deep learning network. This can be also said for some forms of stock trading. In a famous case, the stock of Berkshire Hathaway went up briefly because some algo trading models saw positive news about the actress Anne Hathaway. So we now have an explanation why they went and bought the stock. But in real life, we would not have had the time to dig deep and figure it out. And as long as they make money on average, it is fine. As my late father used to say, you do not always need to understand everything. Or do you? I will not go into that murky and important subject, but it is clear that if you have no idea why the model makes suggestions it does, it is quite probable it may display some biases. It may provide you with some political ads based on your sports and media channel consumption, and indirectly it could offer different ads or content that correlate with your ethnicity or socioeconomic level. And I suspect that is one of the reasons why the internet giants used to say these models are completely unexplainable and we should not even try. They were afraid of what we may see when we open up the black box and look inside. However, the events of the last couple of years have led the public to demand a shift from raw accuracy or hit rate to emphasis on explainability and showing your models are free from bias. So now let's go to more serious matters. When considering mobility, namely autonomous cars, you more often hear claims that those systems are better than regular drivers on average, that they statistically make fewer accidents and therefore we should strive to put them on the road ASAP. However, consider this. If we don't understand how these systems work in detail, how do we know we are testing them in all the right scenarios? Imagine, for example, a volcanic eruption like Mount St. Helens in Washington state several decades ago and the air becoming full of fine ash particles. Do we know how the vision and LiDAR AI will behave? If you recall the Volkswagen diesel emissions fiasco a few years ago, it took the world's most advanced regulator many years to find out a simple programming hack in the engine emission control, because the algorithm in the engine was designed to excel in the simple emission test. Now we are talking about deep neural networks with multi-sensor inputs. How can we be sure if we don't understand how it works? And of course, imagine we have an accident where an AI took the wrong decision. How long until we figure out what went wrong and whether it can happen at scale again?
However, probably the quintessential case is medical diagnostics. At the end of the day, it doesn't matter if you call it a decision support system or a system to automate or replace the physician. Suppose a 55-year-old male, heavy smoker, comes to your clinic and you do a 3D chest CT scan. In the lungs, you find a lump, a nodule. It's quite big. Now you have to decide as the physician if you do a biopsy or not. It so happens that biopsies do not just cost money. When you do them, there's about 1 to 2% chance that they may cause further complications, as some of the people who come in for these tests are not doing very well originally physically. Now you have to put a decision in the hands of an AI that you don't understand. That is a tough call. Will you send someone to a biopsy with a 1 or 2% chance of complications just based on a black box? Okay, so it may come as no big surprise that explainable AI is a big hot topic. In ODSC London 2019, there were 4 sessions about it. Over the last year, the trend became even more apparent. In financial applications as well, people are not content with just make me my money by picking the right stocks. Since they are finding out that when something fundamental in the market changes, such as COVID-19, the models stop working and you lose a lot of money very fast before you even start to understand why. So for example, in March 2020, many of the quant funds relying on AI lost gigantic amounts of money. Clearly, COVID-19 was a wake-up call for some people in the hedge fund industry who were not so concerned before that about what's in the black box. Okay, so let's sum up into a simple rule of thumb before we delve into cases and methods. When you only care about the statistical aggregation of AI decisions and each decision by itself has limited damage or risk potential, you may not need to really understand how it works. If Spotify played you a song you did not like, or the ad you've seen was not relevant for you, no harm was done as long as on average the model is better than the alternatives. But whenever a single decision has implications over human lives or even finance, AI explainability will be more sought after and possibly even mandated by regulation or insurance companies. As a matter of fact, there are already insurance companies offering AI insurance. Now here are 2 very real examples from last year. People have started applying and training AI for medical applications. I hope the resolution over the internet as you are seeing this is good enough. On the left-hand side, you can see some close-ups of suspected moles or skin melanoma. Physicians have trained an AI model for suspected mole detection and then applied it on a different set of data in a different country. Now in that other site, they often use blue markers on the skin to clarify which mole is the one which is suspect and requires further, more detailed examination, or maybe just a second opinion. Some people have a lot of spots on their skin and you don't want any ambiguity into which is the one you are discussing. In the middle photo, the upper and lower dark blue marks were made intentionally by a physician. They are not actual moles. Yet the original AI model was not trained to identify dark blue marks. So when it sees the middle photo, it declares malignant. While if it were shown the original unmarked skin or a close-up of the actual mole, it would declare correctly benign. Now the physician would never make this mistake because they realize that skin is never blue and these are artificial marks. Going back to our explainability criteria, if you have no idea how your model works, you could never know in advance what it would do in such a case. Also, assume you now discover this error or problems. For a physician, after the first time you tell them this is blue, just ignore it, it's a mark, they will take your advice. But how do you train now a new model to take this into account without having to create many more new training samples? Now to a natural language processing example. A lot of the first wave of AI applications in medical data revolve around the extraction of structured data from unstructured reports. That is, from natural language reports. These are used to provide concrete yes or no answers like, has the patient undergone a certain treatment? Was it successful, etc. Naturally, a nurse or a physician would have no trouble reading the report and telling you that, but you want it automatic and at scale. So, a team in Seattle has trained an NLP model to read oncology reports and extract such a single datum from them. And they got really good results and all seemed well. But when they applied the same model to reports from a different hospital in Kansas, the results deteriorated and actually in some cases were totally failing. The technical reason is that medical doctors, in this case oncologists, are people, and people use different phrases and terms to describe the same treatment and outcomes. Now again, the issue was not that the model didn't work, but that there was no simple way to predict in advance or to avoid this phenomenon, because if you don't understand how it works, how can you tell how it will behave on other people writing text? Technically speaking, the area under the curve or the receiver-operator curve may be different due to systemic factors, in this case, the identities of the actual MDs. Just to make it clear, this was not due to poor statistical testing. You can test on thousands of examples, but you cannot test in advance for systemic differences which you do not understand. Worse, in areas like medical diagnostics, by the time you will realize that your performance that should have been 97% is 90%, you probably had to have made hundreds or at least many dozens of applications of your model, which was not ideal. So even realizing you have a problem can take too much time and endanger too many people. So perhaps not surprisingly, the first to classify AI techniques by their explainability was the Defense Advanced Research Projects Agency, also known as DARPA. They made the claim that is now often repeated that, for example, decision trees are rather explainable, while deep learning networks are not. However, it turns out with all modern ML methods, once you scale up in model size, they become a black box. And I will show an example. So here, for example, you can see a binary decision tree used to classify handwritten digits, the MNIST database, which is a famous sandbox example for image understanding. Jeffrey Hinton and associates cleverly constructed it, and it is quite easy to apply. Given an input image, you compute the dot product of the input with the first weird image up there in the middle, and based on the resulting number, you go either left or right based on a threshold. You do that 2 more times with different weird images, and you get a final classification. And it is actually even pretty good. It's not as good as the latest deep networks, but it's not far behind. So, is this process simple and tractable? Yes. Can we feel we understand how it does the classification? I do not think you can say that. So simply put, this is an absolutely beautiful example by the Grandmaster Hinton, showing that the type of AI model and even the size of the model do not guarantee explainability. We are getting near the part where I actually defined what we consider practical explainability and show how to use it in practice. On the left-hand side of the slide, you can see several sentences relating to explainability. Now, the ones that spring most naturally to mind are to understand why it works. And actually, there are several methods like LIME and SHAP that are now becoming very popular and can sort of accomplish that. Essentially, what they do is look at various input fields to the model and try to see which ones affect the outcome the most. Another way to phrase it is they identify the most sensitive input fields and the most effective change directions for those fields to change the model outcome. This way, you can explain the result of a model by saying, you see, if I just omit this word, sneeze, from the patient symptoms list, the flu diagnostics of the model will disappear. And if I remove the dog's head or that part of the electric guitar from the input image, the classifier will no longer classify the image as being that of a Labrador playing an electric guitar. I believe such analysis can definitely help people feel they understand what goes on under the hood, and there is definitely no harm in it. But I also claim it may not be as practical as what I am about to show next. Truly practical explainability has to do with the other 4 sentences. We want to know when the model is likely to succeed or fail, How reliable can we expect it to be? So that under certain circumstances, e.g. X-ray images taken by a specific machine in the hospital or at a certain angle, we may choose to abstain from using it. The ability to abstain from making a decision by the AI is actually far more valuable than it initially seems. In decisions of gravity, we have today people calling the shots. Financial advisors, physicians, they are not going to suddenly disappear. Our AI will assist them, but they are still going to be around. So the best course of action is simple. If you know you cannot trust your AI's judgment on a certain case, just refer this case to a human. Let the AI handle cases where you think it does well, rather than try to cover them all with an imperfect model. So knowing when to tell the AI to shut up and why you asked it to do so is very practical. The other critical need is, when it does fail, we want to know why in a way which will help us actually fix it. At the end of the day, this is what the customers really want. They want to use your software, AI or not. They will encounter an unforeseen issue, and they just want you to know how to fix it. It's that simple. If you cannot fix it quickly and reliably, you have a big issue. True to my original promise, I will now show some practical methods to do this. They will not work on all types of AI problems, and we will make it very clear where we apply them. First, let us consider image classification, segmentation, and object detection tasks. The typical architectures involve several layers of two-dimensional convolutional layers, followed by several fully connected layers. Now let's look at the last layers, in particular the one just before the last final classification or the object detection. It is essentially a vector with n components. The image is long gone in the lower layers. The neurons or vector elements here do not have a simple visual interpretation. Going back to our training set, which was labeled, we ask ourselves, how similar is the new sample in this layer, the one before last, to any samples from the training set? Note, we are not looking for training samples which look visually like the new input, but for ones that their last before layer is similar to the one of the current input. Similarity means some common used measures such as the cosine distance, the Euclidean distance, or some other typical measure of vector similarity. Now here is the point. If we find our new sample is similar in that distance measure sense to several training images of the same class, we feel justified in saying we have seen past examples which are similar to this one. We feel our model knows what to do. But if we find that the similar training images are from several classes, or that the actual distance to the closest available training images is not small, exceeds some threshold, we may say we are not sure the model knows what to do here, or the model just didn't train with enough samples close to this one. In that case, we may choose to abstain, to avoid giving a classification or object detection result. We have tested and used this method first on sandbox models like MNIST, and then in actual medical image classification problems, and found it is clearly superior to traditional methods such as just e.g. using a threshold of the classification neuron results. It is quite easy to implement and can also be done efficiently if you use hash tables. If anyone feels this short, admittedly short, description is unclear, please ask me more on the Slack channel. I'm here and available. As a final note, in all basic courses we are told that the level of the neural network output, the actual number, corresponds in some way to a certainty of this model. If it gives a number close to 0 or 1, the result is high certainty, and a lower one for numbers in the middle. While it is true that the loss function during training attempts to drive the model towards such behavior, there is no reason to believe it will necessarily succeed. In practice, in complex models, the number has very little to do with any amount of certainty or reliability. It is not even a measure of how close is this example to things we have seen before. A research paper by Papernot et al. From 2018 presents a similar principle, but they use it mostly to detect adversarial attacks. Looking at the different layers of the network, they seek similarity between the values of the layer vectors and past examples, and where there is no significant match, they raise the flag. This could be an adversarial attack. Another method which is sometimes used to boost confidence in a model is known as test time automation. It's a great method, we use it as well. However, it does not really provide explanatory power. It just says when we tweak this model a little, we get different results. We have no idea why, we have no idea to which past examples it's relevant, and that we consider a weakness. Now, if we find in the training set input images which are similar to the new input, we can retrieve them and show them to a human operator or AI engineer. If our training set is sufficiently dense, some of them may look also visually similar to our new input, and thus we can make an informed decision if we feel our model can be applied on this case. In many ways, finding such a similarity is often even better than just getting the correct results. Medical doctors are a lot like judges. They hate to innovate. They like to be able to say, my diagnosis, judgment in this case, is based on the one made before me on a very similar one, here it is. So for example, being able to show this nodule in the current image looks very similar to a nodule from our past which was already classified as benign, may be the most valuable and unequivocal decision support aid, even more than the actual model classification result. As a last step, we can then search for a set of image augmentation methods which actually transform a sample from the training set to be visually similar or identical to our new input. If we can find such a continuous transformation, in a way one can claim we have found a definite proof our current classification is correct. You can see an example of such a morphing on a handwritten digit here. But we have all seen morphing operations that take, for example, one person's face and morph it to another. This is becoming very popular. Having provided the find nearest neighbors from training set as an explanation which can help us estimate how much we trust our model on a new given input, we now proceed to the second and even harder to achieve but even more powerful explanation mechanism. That which enables you to actually fix the model when it errs. This is really the key message, the essence of how to obtain explainability that can help you fix your model. However, as we shall see, we only manage to apply it to specific problems, such as medical imaging. So here is a proposed definition or recipe for perfect explainability for a decision, either AI or human. If you can construct a legitimate, continuous transformation from one example we all agree about to the new case, you have perfect explanation. It forces everyone to agree on the current classification/decision. There is no longer any allowed ambiguity. In the animations below, you can see 3 instances of handwritten digits. They are continuously transformed from one example to the other. Now, if for example the first frame is a previously labeled example and the final frame is a new sample, we only have 3 choices or outcomes. A, we agree on the final classification being identical to the original correct one. We are in agreement. B, we agree the original sample was mislabeled and correct our training database. Again, we are in agreement. C, we claim that at some point during the transformation, it became illegitimate, meaning it created some Frankenstein, some image which is simply not a digit. In that case, we have found a new boundary area of our training set, and the said transformation can help us define it with great new training samples. So for example, the 3 animations in a row are cases A or B. But look at the transformation at the bottom of the slide. The left image, a training set sample, is clearly a 7. The input image on the right is a 1. But during the transformation, we created the middle image, which is a classic I cannot decide case. This is not a bad thing. This is a great thing. It made us realize there is a whole category of inputs, which we call SEV1s, like 7 part 1, somewhere in between a 7 and a 1. Now we can do one of two things, and this is a customer choice. We can define them as belonging to one of the two existing categories of 7 or 1 based on our taste, rather the customer taste. Or, and this is a big or, we can say they are not digits. We want the system to abstain from classifying them and issue an alert. I stress again, this is a customer decision. This is the moment where they feel they have real power and perhaps also new insights into their problem. As a side note, one thing I always like asking in interactive sessions is how many categories are there for handwritten digits? And people usually tend to answer 10. Well, it's actually 11. In any classification problem, you have the large cloud of dark matter surrounding the visible galaxies, which are the categories. It is the category of images which do not belong. They are not digits or proper images of lung tissue or of a face, depending on your problem. These are images we should not be classifying as one of the known categories. Just to contrast this practical explainability with more traditional methods, take a look at the right side of the slide. You can see the colored areas in the digits, which are the lime/shap explanations for why the digit was labeled as it was. These are the parts of the image which contributed, according to these algorithms, the most to the classification. They definitely make sense, but if you now have a mislabeled new sample, how can you use those insights to fix it? There is no clear way to apply those interesting insights to improve your model. That is where our method, we believe, is better. For illustration purposes, let's show this in the phase space of classification. Consider this simple illustration. We have 3 classes, could be for example 3 digits. Now it is quite clear we can add many new colored dots, which are training samples, inside each of the clusters. And of course, they will do very little or nothing to improve the classification results. The model has already proven it can classify them. If we apply now our original k nearest neighbors criteria, we will find for such samples inside the category that we are doing well. They have a solid set of previous samples like them, and we are confident and successful. However, the area where we really need to improve our model is in the borders between the clusters. The white background is what we called dark matter, images which simply do not belong to our problem. But what we want to do is find or create new samples which are at the borders, along the black dashed lines. They will help our model retrain and get these corner edge cases under control. Our transformation from one sample to the other is just a dashed line connecting two samples, either from the same cluster or from different clusters. Where the dashed line touches the border, it brings us the greatest value as new samples for training. Okay, so we may think to ourselves, hooray, we solved AI. Not quite. The hard part is finding those transformations. Just to show that this is far from trivial, look at the upper part of the slide. This is a simple pixel by pixel averaging transformation. It is very simple, but it is not very useful, because most of the images it creates are dark matter. They are not valid digits. On the lower half, you can see a useful transformation which keeps the validity of the input all along the path. But how do we find and calculate such a transformation? Well, luckily for us, we can always take advantage of the hard and excellent work of others. In the medical area, continuous transformations and their calculation have been used for years to register images of organs when viewed at different times, angles or under pressure. Body parts are not rigid, they twist, they enlarge, they get smaller or thinner, yet they are still the same organ. So we took the cutting-edge results of people like DeVos et al., cited here, and applied them. They used deep learning to find the transformations between two images and then applied this method first to handwritten digits and then to actual organs. With some required changes dictated by the subject matter, we used the same method. I did say practical in the talk headline, so let's see a way to use this. We have here two real samples from MNIST. Are they a 0 or a 6? I don't have an opinion about it frankly, but when the left one was labeled as a 6 in the training set, and now we have the right one to classify, we create a continuous transformation from the left one to the right one. We apply our classifier to all of the intermediate images as well. Is it steady? Will it always say 6? Will it flip to say 0 at some point? Well, you can see how it behaves. You can also see below the graphs of our k-nearest neighbor's confidence measure changing. Clearly our transformation crosses a boundary area and samples created around it should be added to our training set. Now, of course, just adding samples to the training set does not guarantee automatically that your model will learn them. But empirically, we found out that new border samples are usually learned very quickly by the model, because they help it redefine the decision manifold, unlike way out there samples which do not have a well-defined manifold near them. So the models tend to respond very well to even just a small number of samples at the border of the manifold. So, to summarize, I repeat here the recipe for improving your model and making your customer happy, feeling that the provider can solve the bugs and can improve where I find faults in their solution. First, you train a model. During testing, you find some glaring error, such as Y, according to your customer. You then use the k-nearest neighbor method to find X, a set of nearest neighbor samples in your training set. You then create a legitimate transform from those images in the training set X to Y, the new glaring error, and you label the images along the transform with the customer input. Then you retrain and repeat. If your problem is not intractable to your model, you should see a consistent improvement in the error rate on the found cases, while you should not see a degradation in previously correct classification. And that, of course, is exactly what you want, steady upward improvement. Now to a real-life example. NEC is doing a lot of work on AI for retinal scans. These are used routinely to detect emerging eye disease and treat it, as well as to alert for the potential onset of Alzheimer's disease and high blood pressure effects. The key is analyzing the blood vessel pattern that you see in the picture. The first stage is then to properly segment the blood vessels from the background, which is not as simple as it may seem at first. It turns out, if you try naive training, the models can quickly learn the basics of vessel segmentation, yet they never seem to be able to fully grasp the topological aspects. As a simple example, blood vessels are not supposed to be out there in space, disconnected from anything else. They are not supposed to form loops or knots or sharp 90-degree turns. But how do you teach a neural network those facts? We use 28 by 28 image crops, and for each patch we ask the following question. In our previously segmented training set, is there a 28 by 28 sample which looks sufficiently similar to this new patch? If so, can we apply a transformation from the segmented sample to this new one to reach a valid segmentation? So for example, if our model encounters a segmented blood vessel which shows a loop or a closed circle or a disjoint segment, it is supposed to search for a similar case in the training set via our fully connected last layer method and fail to find one, and therefore reach the conclusion that this is not a valid blood vessel. This slide is just to show that the blood vessel segmentation problem is far from easy, especially when you work within the confines of a fixed size patch. So as we know, humans are very good at seeing the whole picture and applying certain topological considerations based on their experience. Yet it is very hard to teach an AI to replicate this ability. So, we were able, using a rather small publicly available dataset of about 40 segmented retinal images, to use our method to train a 2D unit model, which did very nicely on its own, but still did have the errors associated with not seeing the whole picture, not fully grasping the topological shape constraints of legitimate blood vessels. I will just flash the technical details in the next 2 slides, and anyone who wants to know more is welcome to contact me later. And another one. Now for a nice sanity check of our method. Have we been able to teach the model via continuous transformation from past examples the concept of blood vessel continuity, lack of loops, etc.? On the left-hand side, you see a normal segmentation result. White pixels mean the model found sufficiently similar past examples to those areas, so it feels confident they are valid. Purple areas mean such past examples have not been found, and you can see very few marginal pixels like that. However, on the right-hand side, we artificially, intentionally injected fake segmented blood vessels which happen to look like digits. The model could not find any past examples that look like them, and hence correctly labels them in the color purple. The model has correctly identified those pixels as dark matter, cases it has not seen in the past. Without getting into details, allow me to comment that similar techniques have been shown to be useful, for example, in anomaly detection in cyber defense. When a computer system experiences a cyber attack, it is supposed to behave differently. This is particularly true for industrial or financial computer systems, which are supposed to operate in rather clear margins. So AI that can find no past similar cases and alert to the potential of a new attack is very useful. In computer vision, the same methods can be applied to generate new samples of human figures in various poses and circumstances, as well as to explain why a certain patch in a certain image was classified as a potential human head or limb. This is very useful in low-resolution images or images taken from a great distance, where the actual patch you inspect is not so different from medical images. It is blurry and small and hard to identify without the bigger picture context. And with that, I shall conclude ahead of time and thank you for your patience, and I'm very happy to answer any questions.